I wanted to take a look at a correct or incorrect use question. In this case, we're looking at the rule add, and right away, a couple of almost mechanical things to notice that give you a clue about why this is indeed an incorrect application of add is because add always delivers a disjunction in the main operator of the line that you are deriving. And of course here in line 3, the main operator is a dot. And so immediately this is already just an incorrect use of add. Another clue is when you look at our rules, there's an above the line bit and a below the line bit. The above the line, these are always your ingredients, as I like to call them. Right? Whatever's above the line is the basis for the rule usage, and it's what's already in your proof. Now, below the line is the line that you're deriving. This is the line that you get when you apply the rule. One of the things that this tells us is that in terms of the justification, there's only one ingredient. That is to say, there should be only one reference line here. And so that's a clue too that already off the bat, this is an illegal usage. And so those are two almost mechanical clues about how to use the rules and how to check them, is that you got to make sure that the main operators and the ingredients, this of course for add, it's just a with and whatever operators it has, because lowercase letters again are sentence variables and they stand for any sentence in the propositional logic, including compounds. But make sure your main operators match up. We have a mismatch certainly here. And then also make sure that you're using the rule properly. The reference lines that you're citing actually match up with what the rule is stating as being required ingredients. Now, to be fair, I think this question gets missed simply as almost a mental hiccup, and it's because people think add and they think math. And so they think, lines 1 and 2 are being added together. The rule is called add because what you're adding in is the new disjunct. That's why the rule is called addition. Not because you're putting together two lines, that's CONJ, but because you're introducing or adding a new disjunct. I wanted to talk about question number 6. This one was more difficult, as you can see from the result. And this one really is just about keeping track of definitions. There's a little tip in the answers to the quiz about how to remember this. It's not a great mnemonic device, in fact, but it is the only one that's there. Remember that completeness is like everything. And so the idea behind completeness is that you can prove everything versus soundness, which is that every provable argument is in fact valid. It's easy to get those flip-flopped or back and forth, and so either have it on your note sheet or cheat sheet so that you know it, or just stick with that mnemonic device, or think of a better one and share it with us. I just want to do this very, very, very quickly because I think from some of the problem sets there's a question about why we care about soundness and completeness. Like, why do you need to know that our propositional logic system is sound and complete? And there's two reasons. The most immediate reason is that for us, this is a selling point, if you will, for the propositional logic, that it is complete and sound. The fact of the matter is that not all systems are sound and complete. The propositional logic is one that is both sound and complete, and that's what makes it very powerful, in fact. Now, power is kind of a weird thing, and so this is just a quick diversion to the juncture of math and logic anyway, right? But just as a contrast, mathematics is not complete, and this was proven by Kurt Gödel. So, quick history. In 1910 was the first publication of the Principia Mathematica by Bertrand Russell and Alfred North Whitehead. Bertrand Russell is a very famous philosopher and also social activist and logician and mathematician. He was an anti-war activist, a self-proclaimed socialist, probably one of the most significant thinkers, I'd say, of the 20th century. And Alfred White Northhead was a mathematician and a philosopher. He's amongst theological circles. He's most known for what's called his process philosophy. And Russell was Whitehead's student. In any case, in 1910, there were 3 publications in the Principia Mathematica. They published this tome that tried to precisely state mathematical propositions and to prove that the system of mathematics was complete. That is to say, they were trying to formalize all of mathematics and then prove that it was, if you will, a good system. Now, just to be clear, there's nothing wrong. To say that mathematics is not complete is not to say that there's anything wrong with it. It's actually this question of whether or not it can be systematized, specifically whether or not it can be formalized into a set of axioms. And it was really surprising to everyone that, oh, sorry, my animations are kind of screwed up. Those are pictures of Russell on top, and then Whitehead in the middle, and then of course Kurt Gödel on the bottom. And then along comes Kurt Gödel in 1931, and he publishes the results of his mathematical inquiries, and his first incompleteness theorem proves that Russell and Whitehead's project to show that the system of mathematics could be axiomatized and completely axiomatized was in fact impossible. Specifically, what Gödel showed with his first incompleteness proof was that any system that was powerful enough to formally represent arithmetic, the arithmetic of natural numbers. So think, 2 plus 2 equals 4, and and division, and so on and so forth with natural numbers. That any system powerful enough to axiomatize arithmetic was actually incomplete, that there were going to be true mathematical statements in that system that couldn't be proven. I mean, this is pretty astounding. Again, there's nothing wrong with arithmetic. This is, if you will, meta mathematics. This is about the foundations of mathematics, of being able to demonstrate that the mathematical system is mathematically good. It's not because of math that it matters that the propositional logic is sound and complete, but this just gives you an idea of why these ideas exist, is that they are fundamental features of systems, and not all systems have them. So it is meaningful to say that the propositional logic is both complete and sound. Both questions 7 and 8, I'm going to look at broken or incorrect proofs. The proof in number 8 is going to be very, very close to correct, and the proof in number 7 is a little bit further away. But in any case, looking at these broken proofs will give us a better idea of both how to check rules and understanding the rules, and also how to recover from a broken proof. First things first, I wanted to mention this formatting here. It is fine. It is something that I talk about explicitly in the slideshow from week 4 when you are using Word or typing up your proofs. And especially if you're using something like auto numbering, your numbers are going to get a little screwed up, and that's fine. The thing to watch out for is to make sure that you are consistent. No matter, a proof does need those reference lines. And so if line A is the reference here, then use line A. Don't use the number 5 or something, So it's okay if your numbering gets a little different, but just make sure that you're consistent. The other thing is this symbol here. It is technically incorrect that it is there, but it doesn't bother me at all that it's there. The / means therefore. That's how we use it in our system. The alternative symbolization for therefore is the triple dots. The reason why it's technically incorrect here is because by definition, each line in a proof has to be a sentence in the propositional logic, and this symbol is not part of the propositional logic. Go back to chapter 7 and go back to the vocab and the grammar of the propositional logic, and the only vocab in the propositional logic are capitalized sentence letters, the operator symbols, and then parentheses. Now, it doesn't at all bother me that it's there, and in fact, if it helps you keep track of when you're done with the proof, keep doing it. It is redundant because, in fact, every derived line is the conclusion of, well, specifically the lines that are cited in the justification, but every derived line follows from, that is to say, is the conclusion of earlier lines. And that's just the nature, that's just built into the general format of a proof to begin with. And by default, the last line is always considered the conclusion. More importantly now, as we go to check the proof, the thing that I recommend, make sure that you have your rule sheet or just know the rules and actually write it out. So line A claims to be using DS on lines 3 and 4. So the DS rule pattern is going to look like this or like this. And line A claims that we're using DS on lines 3 and 4. And so you know what? Just to double check, write it out. This is line 4 and this is line 3. Now, when we compare when we focus on what's going on here, we see that the left-hand disjunct occurs in a line by itself with a negation. Looking at the DS rule pattern, that means that we're looking at this side where we've got a disjunction, the left-hand disjunct of which appears on a line by itself negated. And what we're authorized to derive is the right-hand disjunct. So if we look at this pattern here, what we're going to be authorized to derive is Q. And that's what we've done here. We've confirmed that line A is a correct use of DS. So far, so good. What about MT? Well, same process. MT says, given a conditional and the negation of its consequent, derive the negation of its antecedent. Now, right away, we see a problem. MT requires two ingredients. It requires a conditional and then the negation of its consequent. This person has cited only line 2 on MT. Now, as we talked about when we were looking at question number 4 and add, automatically now this rule is done. It's just illegal. But we can take a deeper look just because we are trying to learn the rules and we're also trying to make headway with this proof. So line 2 is this sentence. Q and not R, therefore S and not R. And what line B is claiming is that not R follows validly just from line 2 by itself. And I'll go ahead and tell you it does not. This is in fact an invalid sequence. And you can do a complete truth table for yourself if you want, but you'll find that that sentence 2 can be true when the sentence at line 2 can be true while not R is false. And so this is just an invalid sequence. And so, you know, it's not just this thing about, well, there's supposed to be 2 numbers here. It's because what's being claimed at line B is actually a wrong bit of reasoning. And again, big picture, this is why the rule system is kind of nitpicky about the rules. You have to use the rules the way that they are stated, because it's only by using the rules as they're stated that you can guarantee or prevent invalid reasoning. Now, also in terms of proof construction, just because there's an illegal line doesn't necessarily mean that you have to start over from scratch, right? In particular, as we'll see when we try to rebuild this proof, it turns out that not R is a sentence that we can derive, but just not from line 2. And sorry about that, I lost my animations here for a sec. Let's take a look at line C. You know, I mean, at this point, the proof is already on the wrong track. But for practice, let's just double check here. And with MP, no good. The rule pattern for MP says given a conditional and the antecedent on a line by itself, derive the consequent on a line by itself. Well, first things first, we only have one ingredient when we need 2. And secondly, take a look at what line C is claiming. It's claiming that from the sentence at line A, from Q, this conclusion, S and not R, follows validly. Do the truth table yourself if you need to, but this premise can certainly be true when this conclusion is false. And so this is clearly an invalid bit of reasoning. Now again, does it mean that we just have to ignore all the work that has gone on here? As we'll see when we rebuild this proof, not necessarily, but definitely you can't leave things the way that they are, at least. And then last line to check, just to make sure that we're okay with the rules here. So SIMP says that given a conjunction, derive either the left-hand conjunct or derive the right-hand conjunct on a line by itself. So line D claims that from line C, so line C is S and not R, and we do have the right ingredient, and we do just have the one ingredient that we're going to try to derive S, which is the left-hand conjunct, which clearly is a correct use of SIMP. now there's an important thing to notice is that line D in isolation, if you will, is a correct use of SIMP, but it is resting on its ingredient. Line C, that is an illegal line. So how do we recover from this, these illegal steps? Line A can stay where it is because it is legal. Even if it doesn't end up being a productive line, it is still legal. Now, all three of these actually get crossed out. And even though line D is a legal application of SIMP, it rests on an illegally derived line. How do we recover from this? Well, it kind of depends on what you saw when you got this far, and this is a hypothetical because this isn't your proof necessarily. But in this case, I'm going to guess that someone did see that not R is derivable. And I'm going to say that because it is in fact derivable. Not R does follow, but not from line 2, but from lines 1 and 3 modus tollens. Right? The modus tollens pattern with respect to lines 1 and 3 is we've got our conditional, we've got our consequent on a line by itself, negated, and modus tollens then authorizes the derivation of the antecedent with a negation in front of it. This is a guess on my part, but I'm thinking that someone did read through the premises and see that not R would follow, but they just got the rule citation wrong. Now, we saw earlier why having a wrong rule citation makes this line illegal, because it doesn't, not R does not follow from line 2. But when you're constructing proofs, I recommend very much the process that we just went through. If you thought not R followed, and then you're sort of looking for the rule that does it for you, just check out what you wrote. Do what we just did and write out line 2 on a line by itself, and then try to fit it to the modus tollens pattern, and you'll see that it's a no-go. But if you really did think that not R followed, just take another look and see, are there other ingredients that are going to give you not R? Now, in order to do that, of course, you do have to know the rules well enough. But that's what the rule cheat sheet for, and that's what your studying does for you. What about the next line? Maybe we can just go ahead and write down not S, maybe we can just go ahead and write down what line C is, but just change the justification. Well, here actually we can't, because there's no way to derive S and not R in one line. The rules just don't allow it. But again, kind of checking this proof out and seeing what happened here, what went wrong here, gives you a clue to how to correct it. S and not R is this consequent. So there's an attempt to use modus ponens to derive the consequent, right? Modus ponens states that if you have a conditional and the antecedent on a line by itself, then you can derive the consequent on a line by itself. So, question, do we have or can we get this ingredient? 1, 2, 3, 4, A, B, we don't have it, but we sure can get it. CONJ allows the derivation of a conjunction. That's why it's called conjunction. And that is what we have here. And it's the conjunction formed by the two sentences that are being referenced. So in that case, Q and not R. And then now we have the required ingredients for modus ponens. That's going to be the line of the conditional, which is 2, the line of the antecedent, which is line C, and we'll be deriving the entire consequent, which is S and not R. And then now, either because you are trying to recover from a broken proof, or just because at this point you see it, we're trying to derive S. S, of course, follows from D using SIMP. Now, obviously, whether or not you can recover from a broken proof depends very much on how it was broken, why it was broken, what you were or were not seeing. But I did want to take a look at a few of these because it's a very natural part of the proof process. Sometimes this is a hard thing for students to grasp, that there's a process to proof discovery. And this is just a demonstration of part of that process. We've talked a lot about strategy, we've talked about tactics. Here now you sort of got an attempt at a proof, and how do we recover from that proof being wrong? And one way is, again, just to keep trying, right? Based on, in this case, the person, I'm led to believe by what was entered into the proof, was seeing some of the underlying logic. They just weren't able to fit it together correctly. And so then how do you fit it together correctly? By referring to the rules and actually checking out each of your lines as you go. This proof is more complex, but I'm actually going to go through it a little bit more quickly because we've already seen the work that it can take to recover from a broken proof. Here, this is actually just, I wanted to take a look at this because this is a tactical reminder. And also a rules reminder. This version of the proof, when I look at your proof, I can only kind of guess at what you were thinking. But, from the fact that DN is hopped on right away, but then line 5 isn't used again until line 9, I'm thinking that maybe this person used a really sound tactic, which is whenever you do see two negations stuck together like that, why not use DN? It gets you a sentence that's a little easier to look at. Now, is that, like all tactics, is that a tactic that's going to necessarily result in a useful line? Not necessarily, but it is a good tactic to remember. When you have double negations, maybe try taking them off and see if that easier to read sentence is something that you can use. So like I said, again, I am just trying to think back to what this person was seeing. But I think maybe there was a recognition of a tactic there, and that's great. Now, at line 6, we do have a problem, though. Lines 1 and 3, A or B, then not X or not E. This is line 1, and line 3 is A, and there's an attempt to derive the consequent. And modus ponens, of course, says, given a conditional and its antecedent, derive the conclusion. Importantly, we don't have the antecedent. We have it in meaning, right? The antecedent says if A or B, and line 3 is telling you and A. And so this is something that I've talked about before in regards to replacement rules. When you have what you want, like in terms of the underlying logic, but you don't have it in terms of the symbols, right? Chances are it's a replacement rule that you're looking at to use. Now, here's the thing. Obviously, there's no replacement rule that's going to get us A or B from A, okay? But the tactic was when I have, if I have the underlying meaning but not the exact expression, we use the replacement rule. Well, we've also seen as a tactic that whenever you want a disjunction, think about using add. We want the entire antecedent, so we want A or B. This is no longer going to be line 3. And so, in fact, this is what has to happen here, right? Line 5.5 is A or B, line 3, add, and then this is lines 1 and 5.5. Okay. So did the tactic... did a tactic that we talked about fail here? Kind of yes, because you aren't, you do have the underlying meaning, but it turns out that there's no replacement rule that's going to work. But was there another tactic that is going to help? And yeah, and it's that tactic about disjunctions. If you want a disjunction, think about using add to get that disjunction. And, I'll be the first to acknowledge that knowing which tactic to use when is really, really, really hard. But the answer to figuring it out is just mindful repetition of completed proofs and then completing proofs. And by mindful repetition of completing proofs, I'm talking about that process that I talked about in the discussion section recording from last week. Take a look at a completed proof, look at them one line at a time, and try to reconstruct why that line is the right line. And just to recap, because I think those are a really important lesson at this juncture in learning about proofs, following the tactics are not going to generate a proof for you automatically. You have to have the mental flexibility, which, by the way, is one of the things that the proof skill set is so valuable for, is that it trains your brain on this kind of mental flexibility of being able to juggle multiple tactics and being able to cycle through them and find the productive ones, which in this case would have been using add, and jettisoning the unproductive ones, which would have been to use a replacement rule. Again, it's not easy. Proofs are hard. They are valuable. That the proof finding skill is valuable, honestly, because it is hard, because it takes both knowledge, right? Knowledge of the rule, familiarity and experience with tactics and strategies, right? And then also that, sort of creative or constructive ability to cycle through possible and even competing solutions. Now, for the rest of the proof, 6 is DM. That is correct. There is a triple switch here. Here we're threading out the negation, if you will. So the negation gets written in front, and then the left-hand side switches its value. So from negation to unnegated, the disjunction gets switched to a dot, and the negation again gets switched to an unnegation, which is totally not the right way to describe it, but I'm trying to stick with this triple switch idea here. 2, 7, we've got our disjunction in line 2, and in line 7, we have the negation of the right-hand side, and we are deriving the remaining disjunct. And then finally at line 9, we're using 8 and 5, and this is modus ponens to get our desired conclusion.